Hello and welcome back to the book club for traffic flow dynamics. Today we are going to resume our discussion on spatiotemporal interpolation. And the last time we discussed that we have detector data, stationary detector data, which provide us with time series of speeds, for example, and other variables. And we have observed stop and go waves as indicated by these diagonal lines. And what we want to do is we want to be able to tell the speed at different points in time as well as different locations other than and in addition to the detector locations and points in time when the data was available. So we want to use this input data and produce this as the output in the bottom of this figure 6.1. And this is a continuous field of speed that we want to generate. And to do so, there are two different methods discussed in this chapter. The first one is isotropic smoothing, and the second one is the adaptive smoothing. Now, for isotropic smoothing, this is the main equation for estimating the speed field, where we have a kernel or a weight that we can obtain by looking at the difference between the point of interest x and the xi location of the detector, and the point of interest in time t and the ti, which is coming from the detector. So at time ti, we have a value of speed for uh, for a particular detector, and we want to be compared uh, to the point of interest. We want to know, for example, at 8:30, when there was no detector value available for speed, what was the speed based on the data from around detectors, nearby detectors. And so the formula for the weight or kernel is using the exponential of this expression, where again we are comparing x with xi and t with ti, and also dividing them with smoothing windows in space as well as in time, which are given by sigma and tau respectively. And here is the result of the isotropic interpolation on the right for these detectors. By the way, there is a problem with the alignment of this figure on the left with the lines on here. So these lines are also detectors, but they are not parallel to, actually they are not aligned to the figure on the left. They should be as I talk to the the author of the book. And so this is the summation of all the weights and xt, and that makes a total equation of v of xt as the summation of all the weights into the speed vi, which is the speed at a given detector I, and we are summing it for all the detectors for all values and then dividing it by the sum of all the weights. That's how isotropic smoothing is expressed in equation. And the limitation of the isotropic smoothing is that if the distance between two detectors is larger than half of the spatial distance between two stop and go waves, the isotropic kernel produces artifacts such as Cartan pattern. And we can see that here in figure 6.3, where it is unable to detect the diagonal evolution of this stop and go waves. And so it creates this Cartan pattern. And to understand this in detail, we created an app that shows us what that looks like. So if we open the app here, this is some synthetic data. It's not the same data as the book, but it's close. We have more stop and go waves, and the detector spacing here is 1 kilometer. So for the isotropic method, we are using the sigma of zero point 0.5, which is half of the detector spacing, and the tau of 0.75. And that produces this result where we see those Cartan, egg carton pattern. But if we, for example, uh, increase this width, then this becomes even more worst. So changing these values result in different type of smoothing because essentially it is looking at detectors in space and in time and then averaging their values without considering that diagonal shape that because the stop and go waves are traveling in time, and so when they get to upstream they are doing that in at a different time. And to do this, the equation or the function that is written in R, where we are looking at the X grid, which is the values of the detectors in X. So these are locations and these are time and all the times that are available to us. And then sigma and tau as in the equation. Then we get a complete grid based on these two location and time based arrays. And then essentially what we are doing is we are using that same equation as in the chapter, and then we are summing in order to do the summation here in the equation. And so based on that, we then create the final result and we return it as grid. So this is the limitation of the isotropic smoothing. And the alternative here is adaptive smoothing. With adaptive smoothing method, it does consider that a time evolution of the stop and go waves. And the equation is different because it considers that problem where the time evolution happens. So we are taking t minus ti as before, but now we are also considering this expression of x minus xi divided by c free. So c free is representing the congested traffic, the velocities, the propagation velocities in congested traffic as well as in free traffic. So c free is actually for the free traffic. So we have propagation velocities in free and congested traffic, c free and w. So to estimate the free speed, we again use an equation similar to isotropic method, but instead of considering sigma and tau here, we are considering that time evolution of stop and go waves, where we look at the difference between the detector location and the point of interest divided by the propagation speed in the free flow. And the propagation speed in the free flow does not go upstream, it goes downstream. And that is shown with this green diamond. So the direction here is this way from the bottom left to top right. And as you can see, the propagation of the traffic jam in congested conditions is the opposite way. It's perpendicular to the free condition, where we are going from top left to bottom right. And that is similar to what we see here, where we have these diagonal lines. And so the equation for the congested condition is similar. The difference is that instead of C free, we are considering the propagation velocity of the traffic jam. So we now have two equations, V free and V congested. And then we then use a nonlinear adaptive speed filter where we consider different weights. We consider the weight W congested for the congested speed and 1 minus W congested for the V free speed. So we are weighing them depending on the conditions. And so if there are more congested conditions, then obviously V congested will have more weight. And so this needs to be calibrated. And how do we estimate the weight? This is estimated based on this expression where we have these three parameters. One of the parameters is V star, which is looking at the minimum of the free and the congested speeds. The other one is delta V, which is determining the transition width around VC. And VC is given by, it's defined here. Let's see where VC was defined. Yeah, it is a transition width around Sorry, delta V is the transition width around VC, and VC is the threshold between free and the congested traffic. So these are the parameters in the equation that needs to be calibrated. And so the parameters were given here, and these are the parameters that we used in the app that I showed. So we have sigma of delta x over 2, tau as delta t over 2, and then C free is 60, W is minus 16, VC is 50, delta V is 10. So based on that, if we now go back to the app, and we select the adaptive smoothing method, we have all of these parameters. And you can see that that egg carton pattern is gone. And we now see those stop and go waves as they were shown here on the detectors. Those are also showing up in our estimate of the field of speed. So we can actually look at the result if we change something. So if we change, for example, C free from 70 to 120, that does not make much difference. Remember, this is the propagation velocity that goes downstream in free conditions. What if we take this back and then change the, the propagation speed in congested conditions from minus 16 to a higher speed? And in this case, it makes a bit of a difference. Let's look at it again in two extremes, so minus 30 and minus 5. So here we see that here this is a much lighter slope compared to this one. So here it changes how the speeds are traveling. Because minus 30 is obviously a very fast propagation of traffic jam. Minus 5 is a slower propagation. So let's put this back to minus 18. Similarly, we have VC, which is the transition center. It's looking at the transition between free and congested speeds, and delta V is the transition width. So I think delta V does not make much difference, but if we change VC, it makes slight difference. So here we are back to that Egg-Carton pattern if we use the transition to be very small between free and congested speeds. Because here, if we have more congested conditions, we need to have a higher VC. And so similar to the isotropic method, we also have the adaptive smoothing method that has these two branches, one for V free and one for V congested. And so for that, we are using the same equations as shown in the chapter. And then in the adaptive smoothing method, this is familiar now based on what we did in the isotropic method. We then estimate each branch and then do the summation, and we get this. Now, how do we validate this estimation of the speeds? Because we have created a speed field, but how do we validate it? So one way to validate it is to actually put multiple detectors on the field. So here they have taken detectors and put them on every 10 meters in this figure. And then without any smoothing, this is the result. You can see these individual lines. When we color the speeds, just like how we are coloring this, when we color all of them, then we get this result. This is without smoothing. This is direct result from detectors. And now, if we do smoothing by considering only a few of the detectors instead of every 10 meters, now we consider the values of only every detector at 1 kilometer of spacing, we get this result. So when we compare this result of multiple stop and go waves, it looks very similar to what the actual detector results show. If we increase the spacing, we still are getting good results with 2 kilometer of detector spacing. With three, it's still not too bad, but with four, now we are losing the evolution of the stop and go waves from the top of the figure. And so increasing the detector spacing will then lose information because we are not using all detector information that we have at hand. But this is one way to validate the results. The other section in this chapter is about data fusion, which refers to the process of combining data from different sources. That could be cross-sectional detector data, it could be floating car data, trajectories, phone calls from people who report incidents, and so on. And so there's this example in the chapter where an accident has happened somewhere in this location where we have floating car data information. We also have stationary detector data information. We also have reports from calls from people who are reporting the incident. And so by fusing all of these, you can actually pinpoint where the crash started to happen. So this is one of the advantages of fusing multiple data sources. And so when we have multiple data sources and we want to estimate the speeds, we want to do the adaptive smoothing, we can then weigh different data sources. So here's the equation that is again using the similar equation as in the adaptive smoothing, but now we are also weighting different sources because one source of the data may be more accurate than the other. It may have more precision than the other. And so based on that, we want to provide weightage. And so for that, we use reliability weight RM, and that gives us a total weight where we are using the kernel and RM, which is representing the reliability weight of a data source. And so once we combine all of that, we can then create smoothing. uh, we can do smoothing and then get the results, but considering the different weights or reliability of the data sources. And in this section, they show the step-by-step of how we get to that equation. So the key takeaway here is that we can create a complete continuous surface of the speed based on detector data, or if you have other sources of data, you can fuse that and then do adaptive smoothing, which is much more effective compared to isotropic method, which can create egg and garden problem. So this is it for today, and thank you so much for joining.